Okay, so 1.8 continuity. Continuity. The limit of a function as x approaches a number a, can often be found simply by calculating the value of the function at a. Just find f of a. Functions with this property are called continuous at that number a. So continuity at a number. We will see that the mathematical definition of continuity corresponds closely with the meaning of the word continuity in everyday language. A continuous process is one that takes place gradually, or not. Here's the important thing: without interruption or abrupt change. The Bush family has had continuous power for a century. So here's the definition. It's easy to remember. A function f is continuous at a number a. Okay, so we're talking about continuity at a number. At one particular x value, continuity there. If the limit as x goes to a of f of x equals f of a. Note that the definition implicitly requires three things if f is continuous at a. One is that f of a is defined. That is, that a is in the domain of f. So here's one thing right here that we have to have. That it makes sense to write f of a. The limit as x approaches a of f of x exists. So the left side has to make sense, right? If that limit didn't exist, then the left side wouldn't make any sense. Thirdly, the two things have to be equal. So you got three things in this equation, which gives us the definition. And that is that you got a left-hand side, an equal sign, and a right-hand side, and they all have to, work. They all have to make sense. So that definition, you remember that little equation, and you've got everything you need to know about continuity at a number. The definition says that f is continuous at a if f of x approaches f of a as x approaches a. Thus, a continuous function has the property that a small change in x produces only a small change in f of x. In fact, the change in f of x can be kept as small as we liked by keeping the change in x sufficiently small. If f is defined near a, in other words, f is defined on an open interval containing a, except perhaps at a, right? So here's a, and f is defined on some open interval containing a, except possibly at a. We say that f is discontinuous at a, or f has a discontinuity at a if. Okay, so right, those three lines don't seem to make sense, but then here's the if, and this is what's going to mean that we have a discontinuity. Okay, ready? It's big. If f is not continuous at a. Okay, so there you go. So not being continuous, we call that being discontinuous. Physical phenomena are usually continuous. For example, the displacement or velocity of a vehicle varies continuously with time, as does a person's height. Okay, so velocity is a continuous function. Height is a continuous function of time. Discontinuities do occur in such situations as electronic currents. Geometrically, you can think of a function that is continuous at every number in an interval as a function whose graph has no break in it. So now we're not talking about continuity just at a number a, we're talking about continuity over an interval, okay, which could be, infinitely long interval. You can think of a function that's continuous at every number in an interval as a function whose graph has no break in it. Now here's the thing, here's the definition of continuity that you have known, the informal definition. The graph can be drawn without removing your pen from the paper. Example, figure 2 shows the graph of a function at which numbers is f discontinuous and why. Okay, so you're like, okay, something's going on at 1, something's going on at 3, something's going on at 5, and you might be tempted to say, yeah, but it doesn't matter what's happening at x equals 1. It only matters what's happening near x equals 1. Well, you're used to thinking about limits, but now we're not talking about limits, we're talking about continuity, and now it does matter what happens at x equals 1. It looks as if there's a continuity when a, okay, this a that we're talking about right here, which is an x value, at a equals 1, because the graph has a break there. There's a hole in it, okay? The official reason that f is discontinuous at 1 is that f of 1 is not defined, right? F of a is f of 1 not defined, and so that's why we don't have continuity. Okay, now you might be thinking, oh, I could draw that without lifting my pencil from a paper. Okay, it would go something like this. See, my pen's still on the paper, drawing the open circle, keep going. Okay, that doesn't count. Okay, that does not count. Okay, it's a hole in the graph. Okay, and you can't have a hole, you can't be continuous if you have a hole. The graph also has a break when a equals 3, but the reason for the discontinuity is different. Okay, so at 3 we had this kind of thing going on. Here f of 3 is defined, but the limit as x approaches 3 of f of x does not exist because the left and the right hand limits are different. So f is discontinuous at 3. So it was discontinuous at 1 because the right hand side of definition 1 didn't make sense. Couldn't talk about it. Here we don't, the problem is the equals. Okay, so in this problem, that is at 3, you have the discontinuity because you don't have the equals. Well, you know what's going to come next. What about a equals 5? What about the 5 over here? Okay, over here at 5, what's the deal with that? F of 5 is defined, and the limit as x approaches 5 of f of x exists because the left hand and right hand limits are the same, but the limit as x approaches 5 of f of x is not equal to f of 5. So f is discontinuous at 5. Okay, if you've got a definition, you know, and somewhere it's defined, but it's not, the not equal to is the issue. Now, in this, at 3, I should say, yeah, it doesn't, that's true that it doesn't make sense to talk about equals, because it doesn't make sense to talk about this limit. Remember, you don't have a limit unless your left and right hand limits are the same. And right, the left hand limit has to equal the right hand's limit, and they both have to be equal to a number L, otherwise you cannot talk about the limit. Well, we were not able to talk about this limit, and so at 3 we broke down on the left hand side. Okay.